Welcome back to the deep dive. I'm really thrilled you decided to join us today because we are looking at something that is basically hiding in plain sight.
Yeah, completely in plain sight.
Right. We are going straight into this invisible thermal technology that keeps our incredibly demanding, our high-tech world from literally melting down. You're unpacking the engineering behind aluminum heat exchangers.
It's a subject that tends to just operate in the background of our lives, but when you look at the sheer scale of modern infrastructure, efficient thermal management isn't just a secondary feature.
No, not at all.
In demand-driven industries, it is the absolute bottleneck. If an engineering team cannot manage the thermal load, they compromise the safety of the product, destroy its efficiency, and drastically reduce the lifespan of the entire system.
And we are relying on these systems constantly. To get a real sense of how this operates at scale, we are pulling from a really detailed stack of source material today.
Yes, very comprehensive.
We've got an Industry Insight article published in December 2025, and we're pairing that with the technical product catalog from Eleanor Industries.
Right, the Indian manufacturer.
Exactly. They are a major aluminum extrusion manufacturer established in 2017. And they have built this massive manufacturing footprint across Gujarat, operating out of Ahmedabad, Degam, and Sabarkantha.
Looking through their technical data really grounds the conversation, I think. We all know the basic physics of heat transfer, moving thermal energy from a hot medium to a cooler one.
Sure, conduction and convection.
Right. But what the Eleanor Industries documentation highlights is the immense material and metallurgical advantage of aluminium when you are dealing with extreme, continuous thermal stress. It's not just about moving heat. It is about doing it reliably under brutal operating conditions.
Okay, let's unpack this. Because anyone who has ever looked under the hood of an old car or maybe opened up a vintage radio knows that copper used to be the undisputed king of heat transfer.
Oh, absolutely.
Copper is technically more conductive than aluminum. So it begs the question, why does this 2025 Industry Insight explicitly state that aluminum is the overwhelming modern standard? What forced the entire industry to pivot?
That is the fundamental trade-off that modern engineers have to navigate. You are absolutely right that copper has higher raw thermal conductivity, but aluminium brings a trifecta of properties that copper simply cannot match at scale.
Okay, what's the first one?
The first, of course, is that it still possesses exceptionally high thermal conductivity. It allows for rapid heat dissipation and incredibly fast cooling and heating cycles.
Which means the system doesn't have to work as hard or run as long to drop the temperature of a sensitive component.
Right.
It reduces the parasitic load on whatever is powering the cooling system.
Right, exactly. But the real pivot away from copper comes down to the second major factor highlighted in the source material, which is the combination of lightweight construction and high mechanical strength.
Well, the weight difference is huge.
It is. Aluminium has a truly exceptional strength-to-weight ratio.
This makes perfect sense when you think about the logistics of global manufacturing. If you are building massive, complex cooling modules for a commercial skyscraper, every single pound matters.
Every ounce matters, really.
Yeah. The Eleanor Industries text notes that utilizing aluminum drastically reduces overall system weight. That translates to easier installation, less structural reinforcement needed in the building itself, and significantly lower transportation costs just to get the extrusions from a facility in Gujarat to a job site halfway across the world.
And you get those logistical savings without sacrificing structural integrity. The exchanger frames and heat sinks detailed in the catalog still retain the mechanical fortitude to handle high-pressure fluids, constant industrial vibration, and severe thermal expansion and contraction without degrading.
So we have the conductivity, and we have the strength-to-weight advantage. But conductivity and weight alone don't explain why these specific extrusions are used in brutal outdoor architectural projects or heavy industrial plants. There has to be a defensive component to the metal itself.
There is, and it brings us to the third critical factor, natural corrosion resistance. The chemical defense mechanism of aluminium is quite remarkable.
How does it work?
Unlike iron alloys that rust and flake away, or copper that can heavily oxidize and turn green over time, aluminium undergoes a process of passivation. It naturally forms a microscopic, highly durable protective oxide layer on its surface the moment it is exposed to the elements.
It's essentially a metal that instantly scabs over to protect itself.
That's a great way to put it, yes.
It might not always look highly polished on a 10-year-old coastal air conditioning unit, but that ugly oxidized layer is a chemical superpower. It is the only reason an outdoor AC compressor can sit on a humid, salt-sprayed coastline for a decade without literally turning into a pile of rust.
Which fundamentally changes the return on investment for large-scale deployments. That natural shielding significantly reduces ongoing maintenance and replacement costs. So when engineers run the numbers on high conductivity, low parasitic mass, structural strength, and natural weatherproofing, the shift away from copper makes complete economic and operational sense.
Aluminium really is the undisputed champion of modern thermal management.
Without a doubt.
But having the right material is really only half the battle. The Eleanor Industries catalog makes it very clear that raw aluminium doesn't do the heavy lifting on its own. It's all about how you manipulate the geometry.
Geometry is everything here.
You have to maximize the surface area so the air or fluid has more physical contact with the metal, and you do that through the power of extrusion.
The extrusion process is what unlocks the material's potential. By forcing heated aluminium through a precision die, manufacturers can create incredibly intricate profiles, shapes loaded with internal channels, external fins, and complex geometries that would be impossible to machine out of a solid block.
And the source material outlines how this shaping process has evolved into 4 distinct architectures, right? Each solving a very specific thermal problem.
Yes, exactly 4.
And rather than just listing them out, let's look at the actual problems they solve. So if you are designing an HVAC system for a high-rise office building, your biggest enemy is space. Real estate is too expensive to dedicate massive floors to mechanical equipment. You need high thermal efficiency in the tightest possible footprint.
Which is exactly where plate heat exchangers come into play. These are constructed using multiple, highly compressed, thin aluminum plates stacked densely together.
So they're just packed in there.
Tightly packed. Because the plates are so incredibly thin, engineers can pack a massive amount of surface area into a highly compact volume. They offer unparalleled volumetric efficiency for tight architectural and industrial spaces.
But plate exchangers don't work for everything. If you are designing a standard residential air conditioner or a conventional automotive radiator, you aren't as constrained by a tiny mechanical closet. You need something rugged, economical, and capable of moving high volumes of fluid and air simultaneously.
For those applications, the industry relies on tube and fin heat exchangers. This is the universal workhorse.
The classic design.
Right. The design is straightforward, but highly effective. Extruded aluminum tubes carry the internal fluid, whether that is a liquid coolant or a phase change refrigerant, and a vast array of thin aluminum fins are bonded to those tubes to catch the ambient air flowing across them.
And the catalog points out that these are heavily favored because they are so cost-effective to produce at scale. Again, this is where shedding the parasitic mass of older copper systems really revolutionized basic consumer appliances and conventional vehicles.
Absolutely.
But the technology doesn't start with standard tubes. Here's where it gets really interesting.
You were referring to microchannel heat exchangers.
Yes, the microchannels.
This is where the precision of modern aluminum extrusion truly shines. Instead of using standard round tubes, which have a relatively limited internal surface area, microchannel exchangers utilize flattened aluminum profiles that contain dozens of microscopic internal channels.
I can only imagine the tooling and die precision required at a facility like the ones Eleanor Industries operates to cleanly extrude those microchannels without them collapsing.
The manufacturing tolerances are incredibly strict, but the industry goes through the trouble of engineering these ultra-compact channels because the environmental and efficiency payoffs are massive. The source text emphasizes a critical point here. The microchannel design allows for vastly superior heat transfer rates while requiring significantly less internal volume.
Meaning you don't need to pump as much fluid through the system to get the same cooling effect.
Precise.
And if that fluid is a chemical refrigerant, you are actively reducing the volume of harmful chemicals required to operate the appliance. That is a massive breakthrough for modern HVAC and commercial cooling systems that are scrambling to meet increasingly strict global environmental targets.
It's a huge win for sustainability.
You get a smaller unit, lower energy consumption, and a drastically reduced chemical footprint.
It perfectly illustrates how refining the geometry of the aluminum directly enables more sustainable, eco-friendly operations. But even with microchannels, sometimes off-the-shelf architectures simply cannot handle extreme niche environments.
Which brings us to the realm of custom aluminum heat exchangers. If you are managing the thermal load of a military aerospace platform, Or trying to cool an advanced AI data center where the server racks are generating unprecedented levels of concentrated heat, standard profiles will fail.
In those high-stakes environments, the thermal footprint is entirely unique. Engineers need tailored thermal performance that integrates seamlessly with specialized heat sinks and high-velocity cooling loops.
And that is exactly where specialized aluminum extrusion suppliers step in. They collaborate with the engineers to design and extrude custom profiles that can handle highly specific environmental stresses.
Yes, the collaboration is key.
It is fascinating to see how the geometry scales from a basic home AC unit all the way up to a hyperscale server farm. Let's actually shift gears and look closer at that real-world impact. We touched on HVAC, but it's worth exploring how this invisible technology impacts your daily life.
We can start with the most direct impact, residential energy consumption. We noted the lightweight, highly conductive nature of these extruded fins and tubes. In a modern residential HVAC system, that optimized heat transfer means a compressor and the blower motor experience a reduced mechanical load. The system simply does not have to fight as hard to extract heat from the home.
And when the compressor runs for shorter cycles, it draws significantly less amperage. The direct, tangible result of all this metallurgical engineering happening in Gujarat is a lower monthly electricity bill for a homeowner in Chicago or London. It is a quiet driver of residential energy efficiency.
If we connect this to the bigger picture, there is an even more dramatic shift happening in the transportation sector. The automotive industry is in the middle of a historic evolution, and aluminum heat exchangers are arguably the critical enabler of the electric vehicle market.
The source material draws a sharp contrast here. Anyone who has owned a traditional internal combustion engine knows the radiator is just there to keep the engine block from warping or overheating under friction. It is a fairly straightforward mechanical cooling loop. But the shift to EVs changes the physics of automotive thermal management completely.
It moves from basic engine cooling to highly complex battery thermal management. Anyone following the EV space knows that thermal runaway is the absolute enemy of lithium-ion architecture.
Right.
When you plug an EV into a DC fast charger, or when you are accelerating hard onto a highway, the battery pack generates an immense amount of localized heat.
And it isn't just about keeping the cabin comfortable. If a lithium-ion cell exceeds its safe operating temperature, it begins to degrade permanently. Worse, it can trigger a catastrophic chemical chain reaction.
Exactly. Managing that thermal load is a matter of profound structural safety. Automotive engineers utilize highly specialized, lightweight aluminum microchannel profiles to pull that intense heat away from the cells rapidly and uniformly. It ensures the battery stays within its narrow, safe operating window, which preserves the chemical durability and maximizes the total lifespan of the vehicle's most expensive component.
And going back to the weight factor, in the EV market, every single gram of mass is a penalty on your driving range. Aluminum doesn't just cool the battery. By shedding the heavy weight of older thermal systems, it literally buys the driver extra miles of range. It is the unseen safety net and efficiency driver of the entire EV revolution.
But the demand isn't just coming from consumer goods. The Eleanor Industries insight highlights massive demand from industrial sectors. We are talking about process cooling for heavy manufacturing operations.
Think about the friction and ambient heat generated in textile manufacturing, plastic extrusion, heavy forging, or massive chemical engineering plants.
In those environments, if you cannot control the temperature of the machinery, you don't just damage the equipment, you fundamentally alter the chemical and physical properties of the product being manufactured. A temperature spike in a plastics facility can ruin an entire production run. Regulating that intense industrial heat dictates the consistent output quality of the factory.
These facilities rely on massive, scalable aluminum sinks and custom extruded thermal loops to pull that heat away from the production floor, reducing equipment downtime and preventing catastrophic product loss. And when you look at the sheer volume of aluminum required to support global HVAC upgrades, the EV revolution, and global industrial expansion, it highlights a fascinating macroeconomic trend.
The global supply chain is physically shifting to meet this demand. The source material explicitly points out that this surge in high-tech thermal requirements is directly fueling the rise of Indian aluminum extrusion manufacturers in global markets.
India is rapidly reinforcing its position as a global hub for these specialized materials. Facilities like those run by Eleanor Industries in Ahmedabad and Sabarkantha aren't just making raw metal. They are providing the precision-engineered extruded profiles that the rest of the world desperately needs to hit their next-generation efficiency and safety targets.
Which requires an incredibly tight feedback loop between the extrusion manufacturer and the engineers designing these systems.
So what does this all mean? When a mechanical engineer sits down to actually specify a heat exchanger for a new hyperscale data center or a next-generation EV platform, how do they choose? With all these different profiles and extrusion capabilities, how do they narrow it down?
The source text provides a very clear three-pillar framework for this selection process. The engineer cannot just pick the most efficient design in a vacuum. The first pillar is application requirements. This is where the theoretical meets the physical reality.
They have to look at the strict spatial constraints. A microchannel exchanger might be incredibly efficient, but if the physical housing for the industrial equipment requires a specific form factor, they have to adapt. They also have to calculate the volumetric flow rates, basically how much raw air or fluid needs to physically pass through the system per minute.
Once the physical boundaries are set, they move to the second pillar, thermal performance needs. This is the pure thermodynamic calculation. The engineer determines the peak latent heat and the required heat transfer rate for the anticipated thermal load.
Once they know exactly how many joules of energy need to be dissipated per second, they can work with the extrusion supplier to select the optimal internal fin design, calculate the exact surface area required, and specify the material thickness to ensure the system doesn't buckle under maximum thermal stress.
And that leads directly to the final and often most critical pillar, the operating environment. We discussed the natural passivation and oxide layer of aluminium earlier, but engineers cannot leave extreme environmental variables to chance.
If you are deploying a custom heat exchanger into a highly corrosive environment, like an offshore wind turbine constantly blasted by salt water, a chemical processing plant with acidic vapor in the air, or a desert solar farm dealing with extreme diurnal temperature swings and abrasive sand, the raw metal needs help.
In those demanding scenarios, the engineer will specify advanced protective coatings or highly specialized anodized finishes.
Anodizing is fascinating.
It really is. Anodizing actually thickens the natural oxide layer through an electrochemical process, drastically enhancing the durability of the aluminum profiles without ruining their thermal conductivity. It is a very delicate balancing act of maximizing thermal capacity while ensuring environmental resilience.
It really changes how you view the built environment. We started with the basic reality that extreme heat destroys modern technology. We explored how the industry moved away from heavy copper, relying instead on the incredible strength-to-weight ratio and natural chemical defenses of aluminium. We saw how extrusion technology takes that raw metal and shapes it into microchannels that reduce chemical refrigerants and custom profiles that prevent EV batteries from going into thermal runaway.
It is a profound example of how mastering a single material at a metallurgical and geometric level can solve critical bottlenecks across entirely unrelated industries. The precision extrusion of aluminium is quite literally a foundational pillar of modern sustainable engineering.
So the next time you hear the quiet hum of a commercial server room, or you plug in an electric vehicle, or you simply enjoy the cool air from your home AC during a heat wave, take a moment to consider the invisible thermal engineering making it all possible. There is a global network of precision extruded aluminium quietly absorbing the stress of our modern world.
This raises an important question. Looking deep into the Eleanor Industries source material, there is a specific application mentioned under the power and energy sector that warrants far more attention than it currently gets. The text briefly details the deployment of heat recovery systems in heavy power plants and industrial processing facilities.
These are systems that utilize massive aluminum heat exchangers, not just to vent parasitic heat away from machinery, but to actively capture and reuse that thermal exhaust. They're catching the waste heat before it escapes into the atmosphere.
Precisely. Capturing that latent heat radically reduces overall energy loss through a process called cogeneration. But if we pull the lens back, I want to leave you with a final concept to explore. If these advanced, lightweight aluminum extrusions are making it increasingly cost-effective and highly efficient to capture industrial waste heat at a massive scale, how might this heat recycling concept completely transform municipal planning?
It is a wild thought. Imagine a future where the massive thermal exhaust of a local data center or a manufacturing plant isn't just vented away, but is captured by high-efficiency aluminum heat exchangers and piped directly into a district heating grid to warm an entire residential neighborhood during winter. It completely obliterates the concept of waste heat. It turns an industrial byproduct into a municipal utility. Thank you so much for joining us on this deep dive. Keep questioning the invisible systems around you, and we will catch you next